next up, it is my pleasure to introduce Brian Helmuth. Brian is a professor at Northeastern University. Who I've known and worked with for a long time before I joined NERRS. But Brian's going to talk about a new project that will be spinning up this year in collaboration with Gibner and actually all of the National Estuarine Research Reserves across New England. So without further ado.
Great, thanks, Jake. All right, so in the next 5 minutes, my goal is to get everybody to think like a non-human, non-mammalian animal. So for example, as you take a breath in and a breath out, you're actively ventilating your lungs. You are controlling the rate of fluid flow of your lungs that you breathe. Now let's all think like a sea anemone and think of how they breathe. Take your hand, reach in your lungs, pull it out, stick it over your head, and hold it there. And hope to God that the wind blows, because if it doesn't, you're going to suffocate. And that's the way many organisms, many non-human organisms, breathe in the ocean environment. I'm not going to talk today about gas exchange, but the mechanisms are really similar when we're thinking about temperature. And so a lot of what I'm going to talk about today is how do we think about the interaction of non-human, non-mammalian organisms with climate change, and ultimately how that's manifest through very small scale weather patterns at the microhabitat level. And that plays out in the context of animal body temperature. So if anybody's ever had a basic course in physiology, that really is the master control variable is body temperature. It's the temperature at the cellular level that's determining all these enzymatic processes, everything that ultimately drives the survival and physiological performance of the organism. Then as ecologists and as oceanographers, what we're trying to do ultimately is figure out how do we scale down from all the things that NERRS tries to measure down to that level of the organism, which then scales back up to the ecology of those animals. So again, one of the things we forget about, but if anybody who's ever had a pet lizard knows, as endotherms, as homeotherms, we control our internal body temperature. So that if we have a fever of even a couple of degrees, we're in a lot of trouble. But again, for the vast majority of organisms on the planet, they have body temperatures which constantly fluctuate. They're ectotherms. The way we're taught this, though, in undergraduate classes is that we're taught that this fluctuates with the environment, as if when air temperature changes, magically the body temperature of that animal changes as well. That's not how it happens. There are multiple controls of temperature, from solar radiation, from conduction, with a hot rock for your pet lizard that controls temperature. So ultimately what that means is in the intertidal zone or in the terrestrial zones, during exposure to solar radiation, we get temperature fluctuations of 20 degrees or more over a couple of hours. Moreover, two animals exposed to exactly the same microclimatic conditions have very different temperatures because of how they interact with heat exchange. So what you're looking at here is an infrared picture of a predatory sea star on its muscle prey. They may be 10 degrees different from one another, and neither is equivalent to air temperature. You see the same thing in the graph on the right, where air temperature is in black. The temperature of the animal is actually fluctuating much, much higher. So typically air temperature sets the lower temperature of body temperature, and then the sun raises it above that. Those of you who work in subtidal environments are not off the hook either. So in shallow subtidal zones, you get surface heating and you get cold water brought up through upwelling or movement of thermoclines. So what you're looking at is a high density network of sensors on a coral reef, where again, we think of coral reefs as being very dynamically stable. This is the fluctuation of cold water that's moving up the ridge. We see situations like this in reefs around the world. I'm currently working in Curacao, comparing sites where we have reefs that have been saved by this movement of cold water from the deep water. So what we're proposing to do is to put out biomimics, to put out small sensors to record temperatures that are relevant to animal temperature. And we've done this in other parts of the world. This on the west coast of the US, for example, we've shown that rather than geographic trends or declines in temperature, we see mosaics. What you're seeing on the right is a geographic mosaic in temperature, chlorophyll, and pH On the left, what we show is that even long-term trends over decades are different depending on whether you measure at the animal level or the level of the environment. And so we use these biomimetic sensors. They're about this big. They have batteries that last 20 years. And this is part of a larger network where we have them deployed from Greenland to Antarctica with a collaborator in Portugal. So I have 10 seconds left, and that's why I know Jake is going to creep up behind me here. And I'm going to stop right there because we're going to put these out at the near sites with your help on where to put them.